C.3, prove Fibonacci formula. When we do verifications using that mathematical induction, actually we prove it. Yeah. All right, so we just complete the base case verification. And we did more than that. We did some practice a little bit. Now we are ready to prove it using mathematical induction. Okay. All right, let us make the induction assumption first. Induction assumption. Assume that the formula is true for k in this range between 2 and n. Okay, some number n, between 2 and n. This formula is true. That is our induction assumption. Next, our goal, we need to verify f sub n plus 1 equals that expression. If we can do that, we prove it. We prove that Fibonacci formula is correct. That's simple. Okay? All right. Yeah. So now we need to do the step. Yeah. Not very easy. Yeah. Let's start formula transformation. First, we can apply the recurrence relation. Okay? But when we after we apply the recurrence relation, look at the number here, n subscript n minus 1, and falls in this range, right? Between 2 and n. n minus 1 also falls into that range, right? So we can apply mathematical induction directly here, okay? So the first one by mathematical induction, by induction assumption. Yeah, the moment, induction assumption to be more precisely. Yeah. And the second by induction assumption another time. So we should have that. Okay. Then after that, let us simplify this form a little bit. We take the common factor 1 over root 5 out of the parenthesis and put two polynomial terms or monomial terms together and two fractional terms also together. Okay? Then let us compare with our destination expression. So you can see this part and that part, both polynomials. Okay? That part, this part, fractional expressions. So naturally, we may like to connect them. We may like to connect them in that way. Yeah. That's based on intuition. Yeah. Don't ask why. Yeah. We need to have some intuition. When we work on math, we need some intuition, experience. Yeah, we need that. Yeah. Guess and verify. We may guess first, right? Then we verify it. So let us make our guess first. Guess is, this is our first guess. Okay? Then the remaining, we also want to guess for the fractional part. Okay? So we guess these two identities. Yeah. Next, we need to verify it. If they're both true, then we prove it, right? If both identities are both equality, let me call equalities. If both equalities true, we prove it. All right, so next step. Let's verify one by one. The first one. The first one. Okay. In order to show this, both sides, they have common factors, right? You can cancel out the common factors. Actually, if we start from, this is a property of golden ratio. If we start that, we multiply phi to the n minus 1th power. Then we get our first equality. That is our first equality. It is done. It is correct. Okay? Yeah. So we're encouraged by our correct guess. So our second guess must be correct. We just need to verify it. Okay? So that's simple. Yeah. Our second guess. Now, to verify it this time, I want to use another commonly used method in math problem solving. That is backward thinking. Backward. Work in a backward way. So that's very common. Yeah. Here we use that. By the backward thinking, if this is true, that is equivalent to make this is true. The second equality is true. Why? We just multiply both sides by the common denominator, right? We remove the, denominators, both sides by the common denominator, right? Equivalent, right? Yeah. Two directions we can go equivalently, right? Yeah. So that's the based on the backward thinking. Yeah. Let's do another time. Yeah, because this negative to the n plus 1 looks not very convenient, right? So we want to simplify it a little more. So this time we multiply both sides by negative 1 to the n minus 1 power, okay? After simplification, we get this. And this is our one of the properties of golden ratio. We know it is correct, right? Then, based on the equivalency of the previous formula, so the previous one also correct. Then, based on another equivalency with the previous formula, it's also correct. So all correct, we verified. Then, combine these two together, we complete the last verification step of the mathematical induction. Our conclusion is we proved that the Fibonacci formula is correct. That's all. Okay? That's the guess and verification way to show the Fibonacci formula is correct. So we complete our video C.3, but not done yet. Why? Because we need to, the last video, we need to find this formula without any guess. Yeah, because guess, someone needs to make that guess. Okay? And for this kind of formula, nobody can guess it, right? It's impossible that anyone can make a guess like this. Yeah. We just don't believe it, right? So we need to really find it. So that is our video C.4. Yeah. All right, so let me stop here. Yeah.